In this video, we'll look at an architectural overview of the TCP/IP protocol suite. TCP/IP is a suite of standard protocols designed for wide area networks. TCP/IP protocols map to a four-layer model: network interface, internet, transport, and application. At the base of the model is the network interface layer. This layer is responsible for putting frames on the wire and pulling frames off the wire. The next layer is the internet layer. This layer is responsible for addressing, packaging, and routing functions. There are three protocols at the internet layer. Internet Protocol, or IP, is primarily responsible for addressing and routing packets between hosts and networks. Address Resolution Protocol, or ARP, is used to obtain hardware addresses of hosts located on the same physical network. Internet Control Message Protocol, or ICMP, sends messages and reports errors regarding the delivery of a packet. The transport layer is responsible for providing communications between two hosts. There are two protocols at the transport layer. Transmission Control Protocol, or TCP, provides connection-oriented reliable communications for applications that typically transfer large amounts of data at one time or that require an acknowledgement for data received. User Datagram Protocol, or UDP, provides connectionless communications and does not guarantee that packets will be delivered. Applications that use UDP typically transfer small amounts of data at one time. Reliable delivery is the responsibility of the application. At the top of the model is the application layer. This layer is where applications gain access to the network. Microsoft TCP/IP supports Windows sockets and NetBIOS interfaces between user applications and the transport layer. Windows sockets provides a standard API under Microsoft Windows to many transport protocols with different addressing conventions. NetBIOS provides a standard interface to protocols, such as TCP/IP and NetBEUI, that support the NetBIOS naming convention for addressing. As we'll see, when an application sends data to another host, each layer adds its own information to a header that is encapsulated as data by the protocol in the layer below. When the packet is received at the destination host, the corresponding layer strips off the header and treats the remaining packet as data. The packet is then passed up the stack to the appropriate protocol. Now let's look at each of these layers and how they interact with each other in greater detail. The network interface layer is responsible for merging outgoing frames onto the wire and for pulling incoming frames off the wire. The mechanism that's used varies with each network medium. When the network interface receives a packet from the layer above, it adds a preamble and CRC. The preamble is a sequence of bytes that identifies the beginning of a frame. The CRC, or cyclic redundancy check, is a mathematical computation that is added to ensure that the frame is not corrupted. The frame is now merged onto the wire. When the frame is received at the destination host, the preamble is discarded and the CRC value is calculated. If the two values match, the destination hardware address is examined. If the hardware address in the frame is a broadcast address, or if it matches the network interface, the frame is passed to the appropriate protocol in the layer above. If the value doesn't match the original CRC value, or the hardware address is not of interest, the frame is discarded. Now let's look at the next layer in the stack. The internet layer is where packets are addressed and packaged for routing. IP provides a connectionless delivery service, meaning that a session is not required with another host before a packet can be delivered. The delivery service provided by IP is not guaranteed. Packets can arrive out of order or be lost during routing. Reliability is the responsibility of the higher layer protocols and applications. When a packet is passed down from the transport layer, IP adds its own header to the packet. The IP header includes the source IP address, where the packet originates, destination IP address, where the packet is going, the transport protocol initiating the request, The protocol informs IP at the destination host whether to pass the packet up to TCP or UDP. A checksum value, which is a simple mathematical computation used to verify that the packet arrived intact, and the time to live, or TTL, a value which determines how long a packet lives on the wire before it's discarded. This prevents it from endlessly looping around an inner network. If the destination IP address is identified as a local address, IP transmits the packet directly to that host. If the destination IP address is identified as a remote address, IP checks the local routing table for a route to the remote host. If a route is found, IP sends the packet using that route. If a route is not found, the packet is sent to the source host's default gateway, also called a router. IP on the router does four things. It decrements the TTL by at least 1 at each router, or more if a packet gets stuck at a router due to congestion. If the TTL reaches 0, the packet is discarded. Next, IP calculates a new checksum. Then it obtains the destination hardware address of the next router, and finally forwards the packet. This entire process is repeated at each router until the packet reaches its final destination. If a router receives a packet that is too large for the underlying network, IP will break the packet into manageable chunks. When the chunks arrive at their final destination, IP assembles the pieces into the original packet. This process is referred to as fragmentation and reassembly. Fragmentation often occurs in environments that have a mix of media, such as Ethernet and token ring. Let's look at how this works. An IP packet is received at the router. IP fragments the packet into 3 smaller packets. A new header is created for each new packet, which includes a flag to indicate that other fragments follow. A flag is not added to the last packet because no other fragments follow it. A fragment ID to identify all fragments that belong together, and a fragment offset to tell the receiving host how to reassemble the packet. All 3 packets are routed to the remote network. Even if they travel through multiple routers, packets are only reassembled when they reach the destination host. When the 3 packets are received by IP at the remote host, they are identified by the fragment ID as belonging together. Next, the fragment offset is used to reassemble them in the correct order. Finally, the reassembled packet is passed up the stack to either TCP or UDP. When IP routes packets, it needs to obtain the destination hardware address. IP relies on ARP to obtain hardware addresses of TCP IP hosts on broadcast-based networks such as Ethernet and token ring. When IP needs a hardware address, ARP first consults the ARP cache for the hardware address that corresponds to the destination IP address. If the mapping is not in cache, ARP builds an ARP request frame for the destination host's hardware address. To make future communications more efficient, the IP address and hardware address mapping of the source host is also included in the request frame. The frame is then merged onto the wire and broadcast on the local network. All hosts receive the request, and the frame is passed up to ARP. If the receiving host's IP address matches the requested IP address, an ARP reply is formulated with the requested hardware address and sent directly to the source host. When the hardware address is received, both the IP address and hardware address are stored as an entry in the local ARP cache. The IP packet can now be delivered using the destination hardware address. If problems are encountered during routing, the Internet Control Message Protocol, or ICMP, sends messages and reports errors to the source host. For example, ICMP will send a source quench message when traffic becomes congested at a router. Source quench tells a host to lower its transmission rate. A redirect message when a preferred route is detected. This could occur if a router becomes congested and there is an alternate route available. or a destination unreachable message when there is no route available, such as when a line goes down. The ICMP message is packaged in an IP datagram and routed to the source host. The next layer in our model is the transport layer. The transport layer provides endpoints as a means to communicate between two hosts. In UDP and TCP, the endpoints are called ports. UDP typically is used to transfer small amounts of data. UDP has two main characteristics. It is connectionless, which means that a session is not established between two hosts before exchanging data. Instead, UDP messages can be broadcast so that many hosts receive the message. UDP does not guarantee delivery of messages. Packets may arrive out of order or be duplicated. Reliable delivery is the responsibility of the application. When an application wants to send data to another host, UDP builds a header that includes a source port, a destination port which provides an address for delivering messages, and a checksum value for the data and header. At the destination host, the packet is passed up to UDP and delivered to the destination port. TCP is typically used by applications to transfer large amounts of data. TCP has three main characteristics. First, TCP is connection-oriented, which means that TCP first establishes a session between two hosts before any data is exchanged. Second, TCP assures reliability by using sequence numbers and acknowledgments. Sequence numbers allow TCP segments to be split into multiple packets and then reassembled into the original segment. Acknowledgments verify that the data was received. And third, TCP uses byte stream communications, which means that the data is treated as a sequence of bytes with no message boundaries. To establish a connection, TCP uses a process called a three-way handshake. In the first part, the source TCP generates a header with information about itself and sends it to the destination host. Next, TCP on the destination host returns a list of the same information about itself. It also includes an acknowledgement that it received the source TCP's information. Finally, the three-way handshake concludes when the source TCP sends a final acknowledgement back to the destination host. A virtual circuit connection is now established between the two ports, one on each host. The information exchanged by the source and destination hosts during the three-way handshake consists of the source and destination ports. Like UDP, TCP ports provide an address for delivering messages. An initial sequence number to tell the destination host whether all segments have been received. Window size, which determines the amount of data that each host can buffer at one time. The TCP segment size, which determines the amount of data that can be encapsulated into a single IP datagram. And last, the SYN flag is set to synchronize communications and inform the destination host that a connection is requested. TCP uses a similar handshake process to end a connection. This guarantees that both hosts have finished transmitting and that all data was received. The top layer of our model is the application layer. To gain access to the transport layer protocols, an application uses either NetBIOS or Windows sockets. Windows sockets provide services which allow applications to bind to a particular port and IP address on a host, initiate and accept a connection, send and receive data, and close a connection. Windows sockets supports both connection-oriented stream sockets and connectionless datagram sockets, depending on the needs of the application. Two sockets, one on each host, form a bidirectional communications path. A socket is defined by a protocol and an address on the host. The format of the address is specific to each protocol. In TCP/IP, the address is the combination of the IP address and port. To communicate, an application specifies the protocol, IP address of the destination host, and port of the destination application. Once connected, information can be sent and received. NetBIOS also provides a standard API. Applications written to the NetBIOS interface are independent of the underlying protocol stack. Standards exist to provide this interface over many transport protocols, including TCP/IP, OSI, and NetBEUI. NetBIOS services are provided by NetBIOS over TCP/IP. There are 3 NetBIOS services. The name service resolves NetBIOS names into IP addresses and manages the NetBIOS names owned by a host. The session service is used to establish a NetBIOS session using a TCP connection once the IP address of the destination host is known. And the datagram service delivers datagrams that are directed to a specific NetBIOS name or that are broadcast to a group of names. Let's look at an example of how a session is established using NetBIOS over TCP/IP. A NetBIOS over TCP/IP session is established between 2 hosts using a 3-phase process. First, NetBIOS name resolution using the name service. Name resolution is necessary because NetBIOS uses NetBIOS names to communicate, while TCP/IP uses IP addresses. Second, a TCP 3-way handshake. And third, NetBIOS session initialization using the session service. Let's look at these in more detail. The first phase is NetBIOS name resolution, which is necessary so the 2 hosts will know each other's NetBIOS name and IP address. NetBIOS generates a name query request to obtain the IP address of the destination host. The request is passed through the name service port to UDP to be broadcast. NetBIOS at the destination host receives the request and compares the NetBIOS name to its local name table. If the names match, the destination host generates a positive name query response that includes its IP address. When the source host receives the positive name query response, both hosts know each other's NetBIOS name and IP address, and Phase 1 is complete. Phase 2 is the TCP 3-way handshake. As we saw earlier, TCP uses the 3-way handshake to establish a virtual connection with another host. In Phase 3, the NetBIOS session is initialized. Initialization begins when NetBIOS generates a session request and passes it through the session service port to TCP. The request includes the NetBIOS name of the source and destination host. TCP passes the request over the virtual connection directly to NetBIOS at the destination host. The destination host receives the request and verifies that the NetBIOS name matches its own. If a match is made, a positive session response is generated and returned. A NetBIOS session now exists, and the applications can transfer data. In this video, we've seen an architectural overview of the TCP/IP protocol suite, including how the TCP/IP protocol suite maps to a 4-layer model, how protocols at each layer work both internally and in association with other protocols, and how applications use Windows sockets and NetBIOS over TCP/IP. To ensure optimal performance on the network, it's important to understand the concept of TCP sliding windows. TCP uses sliding windows to control the transfer of data between a client and server. Each TCP/IP host maintains 2 sliding windows, one for sending data and one for receiving data. The size of the window indicates the amount of data that can be buffered on a system. During the TCP three-way handshake, the size of the send window on each host is set to the size of the other host's receive window. Let's look at what happens when a 10K file is copied from the client to the server. For this example, each host has a window size of 8K and a TCP segment size of 1K. The segment size determines the amount of data that can be encapsulated into a single IP datagram. TCP is handed data which is placed in its send window, in this case 8K of data. TCP adds a header with a sequence number to each packet and transmits them to the server. When each packet is transmitted, the client sets a retransmit timer, specifying how long it will wait for an acknowledgement before the packet is retransmitted. A copy of each packet remains inside the send window until an acknowledgement is received. As the packets arrive at the server's receive window, they're put in order by sequence number. When the window fills to a predefined threshold, or two sequenced segments are received, an acknowledgement for the data is sent to the client along with the current window size. Once an acknowledgement is received by the client, the send window slides past the acknowledged data over the data waiting to be sent. If the client doesn't receive an acknowledgement or ACK for the remaining packets within the time set by the retransmit timer, the packets will be resent. If the packets are received out of sequence, the delayed ACK timer may be set to force an acknowledgement. For example, if the server receives only packets 1 and 3, the delayed ACK timer is set for the first segment. If no more packets are received to complete the data sequence, or the window's threshold is not reached, the delayed ACK timer expires, forcing an acknowledgement to be returned for the first packet only. This is called a delayed acknowledgement. When the client receives the acknowledgement, the send window slides past the acknowledged data, and packet 9 is transmitted. Now let's see how window size affects performance on the network. Performance can be improved by eliminating the time that systems wait for acknowledgments, and by minimizing network traffic. Since received data must be acknowledged, the size of the sliding window is important in determining whether a system has to wait before sending additional packets. A window size that is too small may cause significant delays because too much time is wasted waiting for acknowledgments. Let's look at an example of a 14K file transfer using a 1K window size. Data is handed to TCP, which places it in the send window 1K at a time. TCP adds a header, transmits a single packet, and then waits for an acknowledgement. The server receives the single packet and returns an acknowledgement. Since two sequenced segments will never be received, the window threshold will trigger an acknowledgement rather than waiting for the delayed ACK timer to expire. When the client receives the acknowledgement, the send window slides past the acknowledged data. The second packet is transmitted and the client waits again. As you can see, it will take 14 packets and 14 acknowledgments to transfer the entire file to the server. The client has to stop and wait between packets instead of being able to stream them. On the other hand, a window size that is too large may also slow performance. On a wide area network, packets may be lost due to heavy traffic at the routers, which forces the client to resend packets. Let's look at an example of a 14K file transfer using an 8K window size. All packets in the send window are transmitted and their retransmit timers set. During routing, all but 2 packets are dropped. The server receives only packets 1 and 2 and sends an acknowledgement. The client receives the acknowledgement, slides the send window, and transmits packets 9 and 10. The client then waits until the retransmit timers expire for packets 3 through 8. As they expire, each packet is resent and its timer reset to twice the original time. No new data can be sent because there is no more buffer space inside the window. If network problems persist and more packets are lost, additional time will be spent waiting for acknowledgments and repeatedly sending packets. The optimal window size, larger or smaller, will depend on the network environment and the size of data transfers. The goal is for data to be streamed without delay and to prevent redundant transmissions.